Salt, mine, that for salt, fiber. Salt is it has different characteristics. And the salt from the Tharsis volcanic ridge area will apply a different mineral kind of consistency from the general volcanic fields around Mars. Also, any formation of larger volcanic complexes. Tharsis complex. Even it mentioned even in the Big Island, you get volcanoes salt in different phases of the eruptions, different times, different areas, significantly different.
Let me, I know I'm just about a couple minutes early, but let me actually just take this time to sort of reintroduce the track for those of you who are here. My name is Doug Plata, urgent care physician in Redlands, California, and I'm the track chair for the Achieving Earth Independence track. Quick show of hands, how many of you were here in our first half of the track, which was Thursday? Okay, 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 well that's a good sign. Apparently you liked it before, and so now you're back. So for those of you who are new, let me just sort of explain what we are doing with this particular track, because if you're coming in, you may not quite understand what's going on. Our track is a little different than other tracks. Other tracks are sort of like Moon track, Mars track, or Space Solar Power, whatnot, and it's just sort of like, it'll be a bit random, it doesn't matter quite the order. That's not the case with this one. What we're doing is, this is the first time this topic has been addressed at ISDC, of exactly what is necessary to be able to achieve Earth independence, meaning what are the things needed for Earth independence. We actually have, let me show you. So we actually have a checklist that we are going through.
Oops, upside down.
I thought I was in Australia, but so South Pole. So yes, so we're going through these and addressing each of these things. I'm saying you need to tackle these things in order to really achieve Earth independence. And then this is sort of our diagram of where the different sources of each of the things and the processes needed to do, provide everything that you need. Okay. So that's what we're doing in this track, and it's encouraging that as we're systematically going through, and we actually, as track chair, actually reached out to people. We have some people who know about growing food, the chemistry people, and whatnot, genetics and whatnot, and we're able to find people who have some experience and expertise in these areas. And then we're bringing one from each of these areas to go ahead and lay before you exactly our current thinking as we open this conversation as to what can be done to achieve Earth independence really as soon as possible. From when a base is established, how quickly can we try to achieve Earth independence. So let me go ahead and get started with our first presenter. Elliot Carroll is actually stepping in. We really appreciate you doing that. For Alex Ignatia, he was on the schedule. And a lot of really interesting work has been done in terms of, in the laboratory, of going from regolith cymbeline to actually solar cells. And I think that this area is actually one of the most developed of all our areas in terms of the technology readiness level. So, welcome.
And Doug, I should say thank you for actually having us.
Sure.
My name is Elliot Carroll. I am CEO of Lunar Resources. We're located in Houston, Texas. And unfortunately, Alex is on the Rhine River this week. So I'm going to try to step in here and teach you guys about the use of lunar resources for energy generation on the moon. Buzzer receiver. Laser.
Like it doesn't, these filters tend to not work to enhance the size very well.
Well, they work for the lasers, so that's what I want. So if anybody has ever heard Dr. Nadia speak before about lunar power generation, the first thing that you would hear is what you would hear him say is the most critical need on the moon is electrical power, electrical power, electrical power. Whether that be for regular transportation, lunar water extraction, communication, life support, construction, everything requires electrical power. Now with essentially with Phase 2.0 thrust upon us, we at Lunar Resources have been trying to think about what are the requirements for the first lunar power grid. And what is the consensus is that the power grid will need to be scalable. The first missions on the moon will only require a couple kilowatts of power, yet a large-scale base will require possibly megawatts. It needs to be able to deliver electricity to multiple locations. You have base, you have commercial operations somewhere else, you have scientific operations elsewhere. It needs to be able to deliver, communicate power to all those places. Third, there needs to have redundant systems or backup systems. And fourth, it needs to be low cost. And I'll speak about that later on. Now, our best projections right now has us thinking that the initial power demand by 2028 will be anywhere between 100 kilowatts on the conservative side, all the way possibly up to 100 megawatts. And with time increasing to tens to hundreds of megawatts by 2035, and far off in the future by 2040, potentially gigawatts and terawatts. Now the space question. So what are the options to generate power on the moon? And I'm sure every single person in this room knows these options, but there are essentially two to have a centralized power system: solar photovoltaics and nuclear. Now, conventional thinking is that you make these systems on Earth and you transport them to space. But there is an issue in doing so. Now, these graphs are from Lunar Resources' proprietary cost models. And what they are depicting is our projected cost to produce 1 kilowatt worth of power over the lifetime of a power grid. Does that make sense to everybody? On your left is a nuclear power grid, and on your right is the Earth transported photovoltaic power grid. So for a power grid that is 100 kilowatts, our models estimate that it would cost $9.7 million per 1 kilowatt, decreasing only down to about $9 million per kilowatt for a 1 gigawatt power grid. As well, for the Earth photovoltaic power grid, we start off at $4.7 million for a 100 kilowatt power grid, and decreasing to $4.5 million per kilowatt. Now, the important aspect of this isn't so much the cost, but the curvature of the graph. These are linear curves. There are big problems in achieving Earth independence if you have linear cost curves for your power. Now, with a linear curve, your cost of your first kilowatt produced is the same as your last kilowatt produced. Cost of the last kilowatt produced. The cost reduction of your products or resources will have a theoretical limit, and that limit is a factor of launch cost and cost of manufacturing assets on the Earth. Now on the bottom here, so what this graph is showing is the cost of the overall power grid depending on its output, which is here. So for 100 kilowatts, we're estimating nuclear power grid costs just about under $1 billion. And for a Earth photovoltaic power grid, we're estimating it costs about $500 million, which is probably feasible in today's environment with NASA and other folks interested in the moon. However, as the power grid needs to grow, you may need 1 gigawatt of power, which I realize is pretty far off. You're dealing with $9 trillion for a nuclear power grid. That's almost half of the U.S. GDP for a nuclear power grid. And 4.5 trillion for a Earth photovoltaic power grid. And if you remember, Alex's big 3 things when it comes to lunar needs, you must have electrical power. So if there's no economies of scale, with your biggest input you're using to produce power, to produce products and resources, you essentially never make anything cheaper than what you can make on Earth, and thus you'll never achieve independence from the Earth. So, thus the question becomes, how do you develop an exponential cost curve power grid model? And you have to eliminate the largest factors in your theoretical limit, which is the launch cost. And if you eliminate the launch cost, you have to utilize lunar resources, leverage the in situ environment, and make the lunar power grid in situ, essentially live off the ground. And this is why we started Lunar Resources. Lunar Resources was established to develop, deploy, and operate technology to enable for an exponential electrical power grid cost curve on the moon. Now, when we're looking at what type of power grid we would develop in situ, let's look at what's on the moon and what environment the moon is in. So what you have is you have a lot of silicon, you have a lot of titanium, you have a lot of iron, you have a lot of calcium, as well as you have an ultra-high vacuum environment. And then you have high solar energy density on the moon. So silicon plus conductive metals plus high vacuum plus solar energy are the perfect ingredients for a photovoltaic power grid. Now, Lunar Resources, our team has been working on developing an in situ power grid for over 15 years. As Doug mentioned, we're probably the most advanced in a lot of the different aspects you're looking, the track is looking into achieving Earth independence. And so the architecture that we came up with, our team came up with, is that you would extract the elements from the regolith using molten regolith electrolysis, and then deposit the solar cells or fabricate the solar cells using vacuum vapor deposition. Now, how would you go about making a solar cell? And I'm sure many of you have seen this before. The first thing you would do is you would melt the regolith into a glass. Then you would deposit the bottom electrode, and then deposit the pido and the endo silicon. And on top of that, you put the top electrode with the anti-reflective coating, and then interconnect the cells with the thin film emitters. Simple enough, right? Well, fortunately, our team has come up with this a tool, a rover, that can actually do this entire system continuously. And we call this our Lunar Deposition Rover. It is a mechanized thin film growth facility. Not only can make solar cells, but it can make almost a variety of thin films and coatings on the lunar surface. It weighs less than 200 kilograms. It uses thermal energy to melt regolith and vaporize the elements. And it uses photovoltaic panels for motive control and power. And this can continually lay cells on the surface. We just continually pave on the surface of the moon to produce more and more power. And the rover is preloaded with an additional amount of raw materials. We're is our silicon metals extractor. This weighs about 150 kilograms. It comes with its own scoop to extract the regolith and put it into the MRE facility. And this uses the solar cells that the solar field that the lunar deposition rover first creates to power itself. So, when combining these two systems, our surface asset architecture weighs less than 500 kilograms. The systems themselves are made to last approximately 10 years. It provides a scalable power grid. It can construct both localized and central power grids. It has extreme power output. So, for a single rover, it can produce almost a half a megawatt of power on the poles and 250 kilowatts on the equator in the first year. And because you are growing you're growing on the amount of power you're continually making, by year 5, you're at 9.3 megawatts of power and 3.7 megawatts of power from a polar and equatorial respectively, from a single rover again. So by year 7, you can produce 17 megawatts of power, or 6.9 megawatts of power on the lunar surface. And so back again to the cost curves. So with lunar resources in situ architecture, you are left with a near exponential cost curve. Which, if you remember the cost of Earth transportation systems, nuclear was between $9 million per kilowatt, and photovoltaics were around $4.5 million per kilowatt. From an in situ standpoint, you start around $500,000 per kilowatt, and you can get as low as $3,000 per kilowatt using in situ resources, which we believe is the building block for a sustainable lunar economy. So, with that said, I am open to questions. Yes?
You haven't considered the possibility of nuclear, is it because we don't know if there's any uranium on the moon?
We don't believe that's feasible in the far future.
Is that the reason because we don't have any fission material?
There's no, well, so there's two things. Number one, systems to develop that, we believe will exceed the initial investment to a power grid to begin with. And in addition, yeah, I mean, that's the main reason. Jeff?
Great, Elliot. Two questions, I guess. So one is, if you're at the pole, putting them horizontal is not going to give you very much power. Do you have a way of pitching
Yep.
these things on angles?
Yeah, so if I can go with that. So you get significantly more power on the poles than you do in the equator. That's because you can actually deposit directly onto the craters, through the craters, so you have continuous power.
And my other one is more of a comment, which is, I'm convinced that you have a superior economic case, but I do think that you're a little pessimistic in the cost of transporting things from Earth, because, tell me if I'm wrong, but I don't think you assume any reduction in shipping costs over time, which I think would happen with that large boat.
We do have a, and that is factored in conservatively speaking. Now, the cost of everything involved in the model is conservatively speaking too. But still, that cost will always be winning.
Sure.
So,
Because you're dependent on all
Yeah.
the client frequency.
that's the bigger thing that we're trying to work on. Yes, sir.
The issue you brought up, and I guess it has to do with the attitude of the solar cells, how high they are and how heavy they are. So how heavier do these be than a typical Earth-produced solar cell? And wouldn't you need to put them on towers to space far apart, as you've been now showing since 2015, to avoid shadowing of one collector by another? It's not the same as a regular solar array on Earth, where the sun is more overhead, and typically to avoid shadowing, you only have to space them apart about 50% of their width. you have to start, you might wanna have each array like 100 yards apart, connect together with cables. And you've got the tractor sun, you know, it's like this, so you get power most of the time, otherwise don't get power most of the time.
So we've done the trade on that, and what we believe is the most efficient way of making a power grid is actually just to directly deposit on the ground itself. So there wouldn't be a raise.
Is that gonna work?
At the poles or at,
Yeah, we did a big trade on that.
Okay, this would work fine during the lunar daytime.
Yeah.
14 days, but you're gonna have 14 days of nighttime.
Yep.
Okay, so what do you plan to do for energy storage, okay, to make up for that?
Yeah, so we're actually undergoing a very innovative project with a partner company of ours that I'm not comfortable talking about here, but we do need energy storage on the equator, and as well as any Earth transported solar cells. So, of course, any system that you're developing on the moon will have to have redundant systems to begin with. So, further study needs to be developed for those scenarios.
Well, as a corollary question then, is there any way you can make a battery out of the elements that you're talking about? You adequately described you can make solar cells from the elements, but can you also make a battery?
I can say that thin film batteries are being made. Yep,
I was wondering what the efficiency was of each of your solar.
they're low. So what we've done in the lab, we've grown about only 4% right now. About 3 to 4%.
3 to 4%?
Yeah, the theoretical maximum is 15%, and we're about to raise that. So when we're modeling this, we're not assuming full maximum theoretical limit there, but our goal is to reach the minimum of 10%, targeting 12%.
You have to have a lot of arrays.
Yeah, that's the point. We're gonna print the.
Cover
so,
the moon.
So this vehicle is made to print, I shouldn't use the word print, made to deposit 1 meter of solar cells every hour. So it goes about 1 meter an hour. And we just plan to print the big enough field as what people want.
Did you mention what other byproducts are produced in the process of doing this?
No, so there's a lot of oxygen produced. Well, essentially everything in the regolith is extracted.
So are you doing anything with the other elements?
If there is demand to do it, we will certainly do it. Our current MRE system is focused on extraction of just the silicon and the aluminum. But just extracting that itself, we're extracting a lot before that. Now, the next step would be to get the oxygen out, and that would be a next generation system, because to capture the gas is much more of a complicated process. Yeah.
last question.
Has there been any discussion of a steam engine? I mean, you got the heat, boil the water.
Yeah, there's been discussion within our, so most people have forgotten that concept. Like we were actually joking last week, because I was going through Alex's slide, and I was like, what is mechanicalized power? But he was telling me about the steam engine idea. So no, there hasn't been discussion that I've heard outside of our internal discussions, but it is a really kind of cool idea. Ultimately, we don't think, Alex doesn't think it will be successful compared to other systems, but it is a really innovative idea.
Okay, thank you. We have a tradition. Oh, sorry. We have a tradition in our track that when we get done with each of the areas, we ask we can go ahead and check off the topics. Not yet. Yeah, appreciate it. Okay, so let's go on with our next presentation. So I think it's fairly obvious that if we're going to achieve Earth independence, a rather big part of it is actually growing food, right? And so it's a big topic, so big we had to break it up to two different people. So our next speaker is Bryce Meyer. He is representing the St. Louis Space Frontier. Yeah. He is actually... Bryce here, he's actually a fairly broad education. I mean, not only with food, but also with biology, right? Computer science. What else?
Aerospace engineering,
Yeah. So he's going to be. He's got a lot of sort of theoretical and practical experience with growing food and figuring out how it's all done. So I really appreciate you being able to share with us now. Welcome.
Either one works. We're good to go either way. Let's see if I put it up to the screen.
Doug, is Art Harmon here? What happened?
So I mentioned earlier that there had to be, the last guy, he had to switch, so they would swap places.
Okay.
So Art Harmon will be speaking in Alex Ignacia's spot.
Yes, and I got to put it on the screen.
What's that?
Oh, sorry. I tried that. Is it an expanded screen or is it new?
You may need to call the tech.
Oh, did you do this? Function 8?
We'll get it eventually and get there. I didn't want to get in there and actually have to hack it. Keep me now, I teach cybersecurity very so often. Anyhow, food is a big deal, right? Growing food is a big deal. A variety of foods. You're going to have a later speaker, Chris, who's going to actually talk about some more menu options and things like that. I'm mostly concerned with actually getting you food on a plate. And so my talk will be a very quick run through some technologies that are appropriate for a smaller settlement colony. Oh, sorry. Appropriate for a smaller settlement colony, right? So not a giant colony, but I can talk about as things grow, how things change. So you're going to see a large percentage of hydroponics and things like that. Otherwise, other than what you saw in my fish speech if you were in it earlier this week. So talk about how much for 8 people. So that's a teeny colony, but we can talk about what will happen when it gets bigger. I'll talk about what happens when you go to space versus what happens on Earth and why it's so a little more difficult than how growing things on Earth are. Some of the hydroponics, which this is going to lean towards a bit, hydroponics and some bioreactors because it's a teenier group. And then I'll quickly talk about some aquatic animals and insects. If you really want to go into that, we can talk about that in some of my other papers. And long-term settlement planning. If you're into the numbers and things like that, I have a whole body of work on the NSS Space Settlement Journal, which is out there on the NSS website. You can look it up and it'll have all the numbers to your heart's content. Basic human survival is pretty much like this. So this is loosely derived from the NASA Handbook for Life Support. So you'll see the numbers. I messed with them a little bit because honestly what goes into goes out of, if you catch my drift, right? And so people consume roughly, a little more than half a kilo of dry mass a day, but you don't actually eat it like that. You actually mix it with water because otherwise it would just be dust in your hands, right? So roughly 2,000 calories. Would I assume food and drinking? I didn't put any wash water in here, so that's a whole separate discussion, the gray water discussion. You consume almost 3/4 of a kilo of oxygen. Everything that you eat has to be handed off essentially to what we will use as our space farm or has to be somehow locally recycled. So I'm assuming that the space farm is part of your overall recycling strategy. You're going to use the mass from the settlers to actually run back through and essentially, and excuse the expression, go from poop to plate. Go from what comes out of you back all the way around. And if you notice, there's this other fraction up here. So, oxygen comes in, carbon dioxide comes out. And you'll notice there's a little more carbon dioxide than oxygen. That's because those carbons come from your food. Super simplified grade school biochemistry version here. So you notice the left side is anything that's photosynthetic, so algae or plants. Right side is anything that's an animal, a fungus, or you. So you'll notice that there's a couple of core cycles that happen. The oxygen cycle results in some carbon dioxide that comes back around. Water goes in with carbon dioxide in the plant, ends up in growth, and so growth is a one-way valve for a plant, right? Anything that, if the plant is living in the sun, it's growing. That's how it metabolizes. It can't shrink, it has to grow. Right, so everything goes into growth. A little bit of nutrients, which is where the nitrogen comes in. You notice it cycles through the plant, ends up in you, or in an animal. So your food is a source of nitrogen and carbons. You get some water you take in some oxygen. The reverse comes out, and hopefully it becomes this nice, beautiful, virtuous process with some kind of processing that happens, and I'm going to talk about that a little bit. So you notice that the waste have to come out, something magic happens, it ends up as nutrients for the plants, right? We'll talk a little bit about the magic. There's also this bottom thing. So if this was an animal you're going to eat or a fungus you're going to eat, growth goes in with water, comes back around, and becomes a food source on that bottom orange arrow. This is biochem sort of 101, and this is how it loops around on Earth, on the moon eventually, on anywhere we go. Something to think about when it comes to eating plants. Most of the plant isn't something you eat, right? Most of the plant is a little bit that you eat and a whole lot that you don't. And even if you eat the whole plant, like a lettuce, for example, you end up pooing it all back out again, right? Your body actually uses a very small fraction of a lot of different fibrous plants, or even if the case of the grain, a lot of it comes back out again. So you are a mass flow all by yourself, right? What you take in comes back out again, just like I showed in that first diagram. And so what do you do with all the stuff that comes back out? If you had this infinite cycle that I showed you before, what happens is eventually, if it's just a hydroponic garden in you, eventually all the carbon ends up in indigestible mass and cellulose and you die. Right? Because you do not exhale enough CO2 to feed yourself. You just don't. Right? The carbon goes in other places and ends up in waste, ends up in undigestible cellulose. Even cows can't break it all the way down. You have to have something else. That's just a fact of life. So notice, only little bits are edible out of that whole plant. How does it work on Earth? So if you're from the Midwest like I am, you're very familiar with what a farm field looks like, and that's one right behind you, that's a wheat field in the back, in case you're curious, in Illinois in this case. So on Earth, farms are soil-based, and taking things we take in for granted. In this case, you cannot live on bread alone. If you were living on just wheat, that's what you'd be living on, right? So this assumes you got all your calories from wheat for 114 days, which is how long it takes for wheat to pop out of the ground to harvest. How long it takes, 114 days, right? So this is taken from actual data from the Missouri Department of Agriculture and human values from that NASA handbook, and this is how the loop would theoretically close. Now you notice there's this magic little box, and I'll point it out. Right here. So that little red box is the magic that happens inside the soil. So in Great Plains, the buffaloes would stomp all the poo into the ground, it would stomp the leftover stuff in the ground, bacteria and funguses act on it, whammo, wonderful growing grass. Because it turns out the soil is a living organism or biome unto itself, right? Inside of it are a series of bacteria, funguses, worms, bugs, whatever. I'll make you remember the bacteria and funguses because I'm going to talk about them again later. Those are how the cellulose gets broken back down into carbon dioxide and water. So that's what happens on Earth, right? You also notice there's this gigawatt hour of sunlight over the time period of 114 days that magically happens to go into the plant, but the plant doesn't use it all. That's just what falls on the surface. There's 170 tons of water that goes through the plant, comes right back out again as transpiration, and just goes away and eventually comes back down as rain. So about 300 times what actually comes into the plant and is stored actually goes up through transpiration and back out. what we take for granted every time. If you went up for lunch and ate a piece of bread, this is what you took for granted, right? And if you have 8 people, here's the masses that are involved just on an Earth farm. So you notice there's a metric ton and a half carbon dioxide to get you 8 people for 114 days worth of calories. So there's a lot of mass involved here, and I'm not trying to kill you with all these numbers. I'm just saying there's a lot that happens on Earth that we take for granted that we now have to replace if we're going to achieve Earth independence. So, soil is essentially has to be replaced, especially initially, by some kind of hydroponic grow if we want to eat vascular plants. So vascular plants are anything that cycle water from their roots back out the leaves and out into the air again. So if we're going to eat those, we're going to have to replace a lot of what happens on Earth, right? So we're going to start with hydroponics, and then one day, if we have enough enclosed volume, we'll start talking soil. Right? So obviously we want way more than just grains. So luckily for hydroponics, there's been a ton of work into growing a lot of different crops. Very likely you'll be growing vegetables because you can get them continuously in a continuous growth. You can make indeterminate tomato vine, you can get tomatoes all you want. You can grow soy, tubers, grains, potatoes, in case you're curious, NASA did a big study on potatoes. So they can indeed be grown hydroponically. To close the soil loop, you're going to need something that's either a bioreactor or combustion. And the reason is you don't have that nice, convenient soil and the years it takes for that cellulose to break down. You just don't have it. So you're going to have either a membrane-mediated bioreactor that is seeded with bacteria. So the same bacteria that would be on Earth, possibly engineered to work a little faster, but it'd be membrane-mediated, so it's high surface area, small volume, right? You can do that route, and that's what I suggest long-term. If you don't have the time or space for that, then you do some kind of very controlled combustion to achieve the same result, where you release the carbon dioxide and water back into the system. You could also add bioreactors for an additional food source, or honestly, and let's be truly honest about this, if I had to feed you in a room this size for 8 people, you wouldn't have a very big hydroponic farm to provide all your food. It would be box of block A and box of block B, because you'd have that yeast bacterial bioreactor, and the yeast would be some of the mats you'd eat. You'd have an algae bioreactor, and you'd be eating lots of algae. And having done it, that's a pretty crappy way to live, I'm just telling you. So, initially, what you're going to have probably is a hydroponic garden. You're going to try to build your first habitat to have a large enough hydroponic garden to provide a significant portion of the calories. There will be some stand-up time, and probably almost 180 days to a year. You either eat stuff from Earth, or you start talking bioreactors, which can turn out food in about 30 days. So you're going to have some combination of bioreactors, what you have from Earth, and the initial products of your garden. So that's the hydroponic garden. At some point, the larger settlement, with enough time, you'll start talking food animals if you want them. You'll start talking shrimp and fish, right? And I'll get to those. The idea is that you're going to have to reduce the mass to the lunar location and reduce the enclosed volume. And I'm assuming at some point you're going to pull some in situ in to build the troughs, the structures, the pipes that you're going to need to make this all work. So, as I said, the grow at time for the first crop is key. Here's some of the core hydroponic things in a very simplified drawing. There's 2 ways to go hydroponic. So, aeroponic, aquaponic, mix your terms up as much as you want. One of them involves no substrate. So it's a tube with either a mist or a film of nutrient water or a flow of nutrient water going around the roots. So that's on the right. And it's a sleeve. And the guys in Arizona, the guys and gals who work out at the University of Arizona do this at their Antarctica station with their lunar greenhouse, right? They have an expandable greenhouse, sleeve down the middle, plants in the sleeves, racks of them along the side like this. So that's the lowest mass option to ship from Earth to get you growing. The danger of that is that can be very unstable if something happens inside the sleeve because there's nothing mediated between those roots. So, and there's also very much surface area for bacteria or funguses to help the roots do their thing. So it turns out in the Great Plains, for example, or even on my grandpa's farm, because he didn't use a lot of herbicides and pesticides, he had living soil in his group, the bacteria and funguses vastly improve the efficiency of the growth of most plants. In the case of soybeans, there will be no nitrogen fixation on Earth without that. But in in space, we're not worried about the nitrogen fixation, we're the ones producing nitrogen and cycling it through the system, let's say. But you still need the bacteria and funguses to get stability in your system and to improve the productivity. So option B on the left is you start adding substrates of some type. On the moon, those can be ground pebbles. So you can take the pebbles, the leftovers from your material processing that you're already doing to make your solar panels, for example, right, or some other process. You take those pebbles and round them off, you want them about marble size. You put them inside your trays, and now you have bacterial substrate. The other thing to note is between your trays, you're going to have UV sterilizers to make sure you don't have any bacterial, don't have any contamination in case one of your plants gets sick. It's built between all of them. In both cases, the root environment is not the same as the environment, the top part, which is called the aerial part. So the aerial part you want to be CO2 enriched so that it can optimize growth, and it has a lot of light, right? Roots, of course, don't need any light, in fact, don't want it. And it needs to be an oxygenated environment for the roots, for them to for the roots, the bacteria, and the funguses to operate optimally. So there's going to be some kind of oxygen mixing down below, some kind of CO2 thing going on up top. Now, the reason I got this little thing in the bottom, you see that little chunk of root tree in the bottom? So let's say you wanted to grow some kind of tree crop, you don't need the whole tree. You chop off the limbs and you directly feed the limbs using some kind of a mediated hydroponic system. So you stick them in a pipe and you grow essentially the limb with the fruit on it. So that's a last resort option for getting some tree crops. But I recommend that long term, maybe not, you just grow the tree if you have one at a time. But it's a possibility. Everybody in this room has probably seen some vertical farming pictures. There's a ton of them on the web. If you saw the Nat Geo article on vertical farming, there's tons of work on it, which is much better drawings than I have, or even Brian Versteg does. It's much better than this too. But essentially, the thing to note is you have lighting both above and around. If you're slick, you'll notice the arrangement of trays so that if humans were working these would have to be wide enough for the humans to do their job. That includes pollination. So, and if you're not going to have bees, which you're probably not, you're not going to have hummingbirds or bats or anything else, you're going to have somebody in there with paintbrushes doing the pollination for a lot of these things. My cousins used to do it as a summer job. It's doable, right? You need fans to move the air around the plants. You'll notice on the edges of the trays, you have these pipes coming off. So you'll have pumps on the end of the trays. You'll also have injectors to inject oxygen into the tray volume. You'll have gas separators on the outside. You'll have a wide variety of equipment. The number one thing in a space farm of any kind is movement of fluids. So that is your number one energy consumer. Is moving either air, gases, or liquids around. So the thing to remember is how pumps work are a big deal. And in the future, it would be really good if we came up with better pumps than we have on Earth, but the ones on Earth are what I've used for all my calculations. So it's not like you can't get all this equipment right now, you can. You can, everything in here that I've talked about, every element of a space farm, you can find right now on Earth and just assemble it together. Now, would we want it a little more ruggedized? Probably. Would we want to do some of this in situ? Probably. But it doesn't mean you couldn't do it now. You could. Nothing in here you can't do now. I'm going to assume that if you're living in a habitat,